All right, ladies and gentlemen, welcome to 7.3 Multivariate Linear Systems and Row Operations. It's quite a mouthful, but multivariate just means multiple variables, more than what we're used to in linear systems. So you might remember from section 7.2, we were dealing with, actually section 7.1, we were dealing with linear systems with only 2 variables. Now we're going to be moving into 3 variables and possibly even 4 variables. The more variables you have, the more equations you're required in order to solve them. We will be doing some stuff by hand, but we'll also be using the calculator to solve these things, using our newly found friend, the matrix. So let's go ahead and get started. Some of the process takes a little bit of time. All right, so first thing we're going to talk about is something called Gaussian elimination. Named after Carl Friedrich Gauss, a very well-known mathematician. You should look him up if you've never heard of him before. And the only reason, it's one of the things just gets his name on here because he's somebody that kind of helped us out in this study. This is for systems with 3 variables, and if you have 3 variables, you're required 3 equations. And what you want to do is you want to transform the system into what's called a triangular form. Basically, you start with eliminating one of the variables from 2 of your equations. Then eliminate a second variable from 1 of the 2 variable equations. Sounds very complicated. Don't worry, we'll show you an example here. And then you're going to use substitution to solve for the rest. So this gets Gauss's name to it. All right. So let's see here. What would this look like as an example? So let's say we had the system. Get my pen here. Let's back up a little bit so I have a little bit more room. Say we have this system, x minus 2y plus z equals 7. 3x minus 5y plus z equals 14, and 2x minus 2y minus z equals 13. So there's all sorts of things that you can do to this. I honestly think this is a little bit more daunting than using the matrices to solve, but I'll kind of show you what we're going to do here. I could take this top equation, and I could multiply it by 2, and I could multiply by 3 in order to cancel out this 3 and this 2. So recall if we had an equation that looked like this, 3x plus 2y equals 7, and I had x minus 7y equals 4, I would probably multiply this bottom equation by 3, and I would say this was 3x minus 21y plus 12, or sorry, equals 12. And I would subtract the equations, and I would say 23y is equal to negative 5. Now, this is ugly because I just randomly chose numbers. But that's how you would solve for y, because then you would take the y value and then substitute back in to solve for x. So Gauss's process here is just a little bit longer because it's now got 3 equations. So what I'm going to do here is I'm going to take, all right, well, this top equation, I can multiply and get rid of the x's here. So I'm going to have a 2x minus 4y plus 2, oops, let's see if I can write correctly here. Minus 4y plus 2z equals 14. And I'm going to take this 2x minus 2y minus z equals 13. And I'm going to subtract. So I get a negative 2y. I get a negative 3z is equal to 1. Now, I'm also going to do the same thing for the middle equation. I'm going to multiply this top equation by 3. I'm going to say, okay, 3x minus 6y plus 3z is equal to, 21. And I'm going to take this 3x minus 5y plus z equals 14. And again, I'm going to subtract. So I'm now going to have a, let's see, this is a negative y plus 2z, if I could pay attention here. All right, so I have this equation. I have my first equation, which has been unchanged. I have a new third equation and a new second equation. So I've basically created the new system by getting rid of one of the x values of x minus 2y plus z equals 7. I have minus 2y, not plus, minus 3z equals 1. And I have a minus y plus 2z equals 7. And then the other part of Gaussian said, okay, that's the first step of Gaussian. The second step of Gaussian is to get rid of one of the other variables from my two variable set. So I could say, let's multiply this third equation by 2. So I would get a negative 2y plus 4z equals 14. And I'm going to keep the second equation. And I'm going to subtract. And if I subtract, what do I get here? I get 7z equals 13. And then I could solve for z, plug it in to solve for y, and then plug both of those in to solve for x. Now, somewhere along the line, one of my numbers messed up because I should be getting z equals to 3 here. And so I made a little bit of an error. The process, however, is correct. I just messed up my numbers somewhere. So if you find out where I messed up my numbers, let me know. I can go back and change that. All right, so that's the process for Gaussian elimination. But that kind of gets a little bit much after a while. So what we like to do is we like to use matrices. We like to use matrices in this form, or in this type of process here. I'm just reminding you here, this was before. If you get 0 equals 0 or 7 equals 7 or anything like that, that means infinitely many solutions. Or all solutions, really. And if you get things like 0 equals 2 or 6 equals 7, that means no solution. All right, now let's look at how we're going to use matrices to solve these problems. And we're using what's called an augmented matrix. And it's a matrix that includes the coefficients from the equations and the numbers from the right side of the equal sign. We're going to make sure that we use placeholders, the number 0, obviously, for any missing variables. If you were to talk about the coefficient matrix, that's the matrix with just the coefficients, obviously. We're going to use the augmented matrix just as we would with a system of equations, where we were multiplying an equation by a number and then we were subtracting. We're going to do this, and we're going to get what's called row echelon form. It's a system of our matrix. It's a look of our matrix where the rows consisting of entirely zeros, if there are any, are at the bottom, and the leading number on each row starts with a 0 and goes to the right. So basically looking like this: 1, blank, blank, blank. It could be anything. These could be anything here. Any type of number. But the difference is this must be a 0 and then a 1 and then blank, blank. Could be, remember the blanks could be anything. And then 0, 0, 1, blank. This is row echelon form. We have something else called reduced row echelon form, where these three, and I'm going to talk about this later, those 3 spots there become 0. And this is the same for any size matrix. Right now this is a rectangular matrix with, what is this, 3 rows and 4 columns. And what we can do is, like I mentioned, you may use any combination of the following. You can interchange any 2 rows. You can swap row 1 with row 2 if you want. Sometimes that's nice if one of them already has a 1 where you want it to have a 1. You can multiply all elements of a row by a non-zero real number. Multiplying by 0 would make no sense at all. And then you can add a multiple of one row to any other row. Just like we did with the Gaussian elimination. So what I want to do here is solve this system using an augmented matrix. So I'm going to write my matrix probably right here in just a second. Let's just go ahead and write it right up here. I'm going to get rid of this stuff here. I'm kind of letting us know that x equals -2, y equals 7, and z equals 3. Just kind of so we know where we're going here. Now this is the same one as we did before, and hopefully this time I'll get it right. What I'm going to do here is I'm just going to look at the coefficients and my equal piece here. So the coefficients for the first equation is 1, -1, 2, and then the -3 is my equal sign. My next equation is 2, 1, -1, 0, and my last equation is -1, 2, -3, 7. Now, you do have to be careful. In this case, it was all x, y, z number, x, y, z number, x, y, z number. You have to make sure that you have an x column, a y column, a z column, and then the equal to part column. So notice we don't use any x, y's, and z's in this. We're just going to use the coefficients themselves. Oops. Darn. All right, so what we're going to do here is some matrix operations. Now, this is how we're going to do a matrix operation. I'm going to rewrite this down here because I didn't know this was going to come up here. All right, -1, 2, -3 again. Now, how we're going to do this is, since there are 3 rows, if you write your things on paper correctly, you can actually use 3 rows of your lined paper, right? This makes this a lot more simple if you spread out. Don't try to shrink this stuff down. But here's what I want to do. I want to eliminate the first 2 things here. I want to eliminate this 2, and I want to eliminate this -1. So eliminating the -1 is pretty simple if I use my first equation. So I'm going to say I want to take row 1 and I want to add it to row 3. And notice I put it next to row 3 because that's the thing that I'm replacing. So if I took row 1 and added it to row 3, 1 plus -1 is 0. -1 plus 2 is 1. 2 plus -3 is -1. And -3 plus 7 is 4. Now that was simple enough. But sometimes I like to do more than one thing in the same step here. So what I'm going to do now is I'm going to do something to row 2 as well. I want to get rid of this 2. So if I took a -2 times row 1, that would make a -2 in this spot, so I can cancel that. And I'm going to add it to row 2. So this now becomes a -2 plus 2, which is 0. This becomes a +2 plus 1, which is 3. This becomes -4 plus -1 is -5. And this becomes +6 plus 0 is 6. And I'm going to keep my top row. And hopefully you see why. I want a 1 in this spot. So I really want 1s here, here, and here. And then I need to get rid of that 2, that -1, and eventually that 2 there. But notice they've changed numbers, obviously. Okay. Now you notice we're not done, obviously. So I'm going to keep row 1 again. I'm going to say it's 1, -1, 2, -3. I'm not going to change that because it's got the 1 where I want it. But now I need to get rid of this 1. But notice that I actually want a 1 right here. So what I'm going to do is I'm going to swap row 2 and row 3. So I'm just going to swap them out. I'm just going to say, okay, this is 0, 1, -1, 4. And this is, I'm going to make this a little bit smaller because I need a little bit more room. So let's say it's 1, -1, 2, -3. I'm going to swap row 2 and row 3. So you can put this here as a row 2, 3. You can say a swap here. 0, 1, -1, 4. 0, 3, -5, and 6. Now, you notice I put back in these 2 rows because these 2 rows are actually what I want. Now what I need to do is I need to get rid of this 3. Well, I can do that by saying -3 times row 2. I don't want to do row 1 because then I'm going to get this 1 plus 0 and then I'm going to mess up my zeros here. So if I take twice or 3 times row 2 and add it to row 3, this becomes a -3 plus 3, which is 0. So I get my 0 already. Get that 0, that's good. Well, this becomes a +3 and a -5. So that becomes a -2. And this becomes a -12 plus 6, which is a -6. And we're actually almost done here. So I notice that this is 2 and 6, which means I can divide. I can say, let's take a -1/2 of row 3. And we've actually completed the row echelon form. Now, some people are like, wow, that was a lot of math, and I have no idea what we just did. Well, what we did was exactly what we did before with the x's and y's and z's when we just tried to solve the equation. The problem was I did my numbers wrong. I don't know what I messed up on. But notice this. This says with no x's, no y's, and 1 z equals 3. Well, guess what? Z equals 3. Now, essentially from here, what you could do is just said, oh, if z is 3, I could rewrite my equation. I can say my equations look like this now. X minus y plus 2z equals -3. I have a y minus z equals 4. And I have a z equals 3. And then I can substitute back in and find my x and y. However, I'm going to jump the gun on us a little bit. And I am going to show us reduced row echelon form. Since I already have a problem in row echelon form, I'm going to go down to reduced row echelon form, where I get rid of, I need to get rid of this, this, and this. So let's go ahead and do that. In order to get rid of this -1 right here, pretty simple, I can just say, oh, let's take row 2 plus row 3. Now, because row 3 is already perfect where I want it, I'm not going to do anything to it. But now row 2 plus row 3 becomes this, 0, 1, 0, and then 3 plus, right? 1 plus -1 is 0. 3 plus 4 is 7. Notice what I just got. 1y is equal to 7. That means I've got the second half of my, or second part of my answer. But again, I like to do 2 things in one step. And since I've eliminated that, let's go ahead and eliminate the 2. So I can say -2 row 3 plus row 1. And nothing changes when I do these two zeros, so I still get a 1 and a minus 1. And now I get a negative 2 plus 2, which is 0. That's good. And then I get a negative 6 minus 3, which is a negative 9. All right, so my bottom two lines, my bottom two rows are now perfect where I want them for reduced row echelon form. But now I need to get rid of this negative 1. And you notice here I can get rid of the negative 1 with row 2. So I'm going to say row 2 plus row 1. I get 1, 0, 0, negative 2. And you notice what we get. X is negative 2. So the solution is, therefore, negative 2, 7, 3 as a coordinate x, y, z. Is this going to take you a long time to do? Probably the first couple times. But it's something we have to do in order to really understand what we're doing here. All right, so I talked about redo row echelon form. It's an easy way to read the solution. That's what I just did. I got the 1s across the main diagonal with 0s everywhere else. If you were to get 0s across the bottom line, that would mean there are infinitely many solutions. The last thing I'm going to talk about here is using inverses to solve systems of equations. What you need are 3 matrices, basically. What you need is a coefficient matrix. Now, this is going to be kind of a calculator thing, even though I'm going to want you guys to do small ones. You're going to need a coefficient matrix, which has to be square. That's why if you have 3 equations or 3 variables, you need 3 equations, that sort of idea. You need a variable matrix, which is not square. And you need a solutions matrix, which is not square. If you were to take matrix A times matrix X, you will get matrix B, which is the idea. Now, if you were to take the inverse of A and multiply it by B, you'll get matrix X. So essentially what I'm saying here, yes, done by calculator, if you were to be given the equations 3x minus 2y equals 0, and negative x plus y equals 5, you could set up a matrix equation by writing the coefficient matrix, multiply it by the matrix x, y, and that's going to equal 0, 5. Because 3x minus 2y has to equal this 0. Using our matrix multiplication, it tells me 3 times x plus negative 2 times y equals this entry up here with the 0. So that's saying this first equation. But with our understanding of inverse matrices, I can say that the matrix xy is going to be the inverse of this. Well, the inverse of that is the 1 over the determinant. So let's see, 3 minus 2, which is 1. Oh, that's nice. Times the matrix 1, 2, 1, 1. I'm pretty sure that's the right. I'm trying to do this off the top of my head here. And so we would do the matrix 1, 2, 1, 1 times the matrix 0, 5 by hand is not too bad. We would get the matrix 0 plus 10 and 0 plus 5. And what this tells me is x is 10 and y is 5. Oops, where'd my 3 go? Ah, that's what's wrong. Lost my 3. That's supposed to be a 3. That's supposed to be a 3. Okay, 3, 3. I thought I had too many 1s there. That makes 15. Got it. All right. All right, so we could do this and find that x is 10 and y is 15. And notice that might have taken a little bit less time than actually finding using the substitution or elimination. But I've had a lot of practice with matrices, more than you have. All right, I do want you guys to do the 2x2s by hand in order to emphasize the process, as I mentioned there. But a lot of it's going to be done on the calculator. Do not just go straight and do all calculator work. When it says put the thing in row echelon form, you actually have to do it. When you have to put things in reduced row echelon form, you actually have to do it by hand. You cannot just plug things into calculator. All right. Slight change on the homework, but I don't think I changed this in the assignment sheet. If it says that you did number 21, please change it to number 22. And if it says 51, please change it to 49 if I forgot to change it before printing those off. Okay, that'll be it. I will see you guys tomorrow.